So thank you for inviting me. Yeah, so this is a talk on the initial NIST post-quantum cryptography standards and what's next. Looking throughout the conference, I may be the only cryptographer here, so hello. Like she mentioned, I guess I'm a crypto lead at MITRE in Virginia. I'm also a professor at University of Maryland, College Park, teaching cryptography. And previously, I was on the NIST PQC team from 2018 to 2022, where we worked on this kind of stuff. So the agenda for this talk, okay, three things I want to kind of convey. The first was this NIST PQC project. Some people in the audience may have never seen this before at all. Some people may know about it. Some people may have been following it, but I want to kind of go through from 2015 to 2022, what's happening in the modern world of cryptography. So there's this process for standardization of new stuff. There's an impact in future that I want to talk about. And then a big lesson learned, really focusing on, geometric algebra researchers. And, there's sort of a lesson here of like, there is something to get out of, geometric algebra for cryptography, for post-quantum cryptography. And I guess the broader world here really wants your input, but you have to be careful with your crypto math. And finally, I'll point out some kind of big challenge problems, right, for the community here to think about doing research in, if you're interested, right, of course. So that being said, let's kind of launch into this, right? So here's the overview of the NIST PQC project. I have a nice haiku for you. It's great that someone quoted Jabberwocky on Zoom just before this talk. So here's my haiku: quantum algs coming, RSA dead, D-log 2, help. What do we do? Okay. So in particular, there's this idea of the quantum threat to cryptography. So if you go back to, the 1970s, public key cryptography has relied on the computational hardness of the RSA problem, on the hardness of computing discrete logarithms. And that's sort of the foundational mathematical basis for the internet, okay? But there is this idea of the quantum threat from Shor's algorithm from 1994. That basically says, hey, if you have a large-scale quantum computer, then you can compute prime factorization and solve the RSA problem. You can also solve discrete logarithms efficiently, much more efficiently than would ever be expected otherwise. And this is going to kind of undermine the integrity of the internet itself. The thing that I'm using to talk to you right now, right? That kind of thing. And so something has to be done about this. And in particular, the underlying cryptographic algorithms that we use for communication on the internet need to be swapped out. And so this kind of leads us into post-quantum cryptography, cryptography that exists after a quantum computer at scale is fully developed. And I should point out here, of course, that, Google, I believe, claimed quantum supremacy about maybe 2 years ago. Quantum supremacy being the idea of they have a quantum computing device that performs some computation that provably no classical computer could ever do within a very long time. In their case, like 200, 500 years, something like that. It doesn't matter how big your large scale classical supercomputer is, it will never be able to compute the thing their computer did. So quantum supremacy has been claimed to be achieved a couple of years ago. So now with PQC, NIST is really sort of jumping in saying, well, we have to swap our stuff over. So quantum supremacy has been achieved, but practical attacks on real world cryptography have not yet been achieved, but they're coming soon. So NIST is far in the process of standardizing new public key cryptographic algorithms to replace the ones attacked by quantum computers. There are really kind of two types of algorithms, right? There's kind of public key encryption and key exchange. This allows people who use these algorithms to sort of have a a private channel, establish a private channel to communicate with someone. And then digital signature schemes. This allows you to authenticate that you're talking to the right person. There's a whole variety of mathematical families here: lattice-based, code-based, multivariate-based, isogeny-based, symmetric crypto-based, right? This was an international process with submissions from all over the world that has lasted years and years and years. And in particular, on the next slide, here's the timeline, right? Beginning in April 2015, 7 years ago, right? There's this workshop held by NIST in Gaithersburg, Maryland, kind of scoping out the seriousness of the issue. And this led to, in February 2016, a NIST PQC call for submissions internationally. Send your best quantum resistant algorithms to a process where we're going to sort of play American Idol, if you will, okay, or whatever it is, right? We're going to have judges and have this kind of public process for many years to evaluate and choose and standardize the best way to do quantum resistant cryptography to replace RSA and Diffie-Hellman, that kind of stuff. So November 2017 was the deadline for submission. April 2018 was the first conference. This was the point where everything had been submitted. This is in Fort Lauderdale, Florida. Okay. January 2019 was the first cut, right? So there's the first round report on, I think, about 70 candidates. And it cut down to about 25 to 30 candidates, something like that. So the second round candidates were announced. August 2019, there was another conference, this time in Santa Barbara, California, co-located with the Crypto 2019 conference, I believe it was. It's kind of the flagship conference of AICR, the International Association of Cryptological Researchers, at their flagship conference in Santa Barbara. So there was that second conference. Then there was another cut in July 2020 after a long period of research. This is not only research papers being posted and peer reviewed, it's also the entire time with a Google Groups forum where people discussed issues back and forth. Not peer reviewed on that case, but still like open communication the entire time. So there's this final thing of this final cut down to the third round in July 2020. And then going into June 2021, there was again another conference, this time virtual. We were in the middle of the pandemic, but we had, I think, 500, 1,000 people or something like that, that kind of range on that conference. And then another, I guess, full year passed or so. And finally, in July 2022, so just recently, like very recently, the algorithms to be standardized were announced, the initial ones at least, as well as some additional ones moving to a fourth round for future consideration. Okay, so this was kind of the announcement of like, hey, this is the fundamental algorithm, in this case, Kyber replacing RSA. And then coming up in the future, 2023, there's this on-ramp for signatures next summer, a fourth round that's going to go on with the stuff coming out of the main process. And then the standards will be finalized, I would say, here in maybe about 2 years from now. Okay, that will be a FIPS thing. It'll be posted on the Federal Register and so on. So here's sort of a summary of the third round situation. Here's the whole bucket of algorithms. You can see lattice-based, code-based, super singular, isogeny-based for key exchange. And then for digital signatures, you have lattice-based, multivariate, hash-based, and zero-knowledge proof-based. So the first thing that happened was that a number of schemes got broken. The two on the right there, multivariate, got broken very early in the third round. SIKE got broken just at the end, and in fact, just slightly after the decision process. So I'll talk about that in the second part of the talk. Then these schemes were chosen to be standards. There's one encryption scheme and 3 signature schemes. 2 lattice-based, they're relatively efficient. Sphinx Plus is a slow but very security conservative, security conscious kind of option. After those were selected for standardization in the green boxes there, and those 3 were broken, additionally, those things were thrown out. So here we have the other lattice-based chems or other lattice-based encryption schemes, as well as the other scheme Picnic that was really competing with Sphinx Plus. And in terms of this code-based thing, this is going to kind of proceed to a fourth round analysis that's going to sort of proceed onward. Probably one of those will be standardized in the future for a second encryption scheme based on different properties. So here's kind of a lesson, right, from this whole process. And I just skirted right past that in 10 minutes, right? 10 minutes, 7 years, right? This whole international process involving, goodness, like 30, 40, 50 countries or something like that of like researchers internationally. The lesson is your algorithm is never totally safe, right? And there's some nice memes from, if you recognize it, great. If not, no worries. But here's kind of the idea, right? SIKE was the scheme that had made it all the way through and was almost about to be standardized. It was seriously being considered right at the end of the third round after 7 years of international analysis. SIKE is super singular isogeny key exchange, right? It's based on isogenies, curves. There's these very beautiful mathematical pictures of like all the beauty of the mathematics of the scheme. Isogenies are mapping curves E1 to curve E2. So each of these points on these circles are elliptic curves, if you understand that notion. And the maps themselves, the lines are morphisms of curves. And it's presumed to be hard to compute certain maps, certain isogenies between different curves. This problem was originally posed by Microsoft researchers at Microsoft Research, so the cryptography group there. And it really was a focus for many years, actually, all over academia, industry, and government, like this idea of isogeny-based cryptography. Again, it was on the verge of standardization. And then, I'm going to kind of talk about this horrible break here. And I'm going to throw up a fun picture and say, hey, I'm not an isogynist, nor I assume where you are, right? So the idea here is, we can't put the broken part in the machine. It wouldn't smash the right tiny things together. Then the machine might break. That would be very bad, right? So this is going to be a very simplified discussion of this break. It is extremely mathematically complicated. But anyway, the point is, yeah, SIKE blew up spectacularly. There's massive fireworks in the cryptography world. There's a paper posted by 2 researchers, Wooter and Thomas, at Katie Leuven in Europe. And they basically took the underlying components of SIKE, which was the SIDH protocol, and they came up with a new idea of this glue and split theorem, Dudekani, from the early 90s. And somehow this theorem from the early 90s that was publicly available had been overlooked for years and years and years. Like even after 7 years of public analysis with focused analysis, this scheme went back, well before that, well before those 7 years. And no one had kind of noticed this. But the main thing to kind of think of here is that they can break the encryption scheme in 1 hour on a single core. Yikes! Right? That's not the kind of thing you want, right? For privacy of your data on the internet. Surely you want more than 1 hour of privacy if you send your password to Facebook, if you send your password to gmail.com, if you send your password to bankofamerica.com, right? Whatever you need privacy for, your sensitive data that allows you private access, you need more than 1 hour of security of that data. So SIKE was expected to allow for over 100 years of security, and it's only 1 hour. There was this kind of unofficial reaction from the NIST PQC team, right? This is the largest mathematical break of a cryptographic algorithm in my lifetime. It was almost standardized after years of analysis. Then it was totally destroyed. So this is a massive surprise, even to people that were kind of completely in the know. So the takeaway from this, from the SIKE, lesson, right, being the largest break, ever, even after all that years of analysis. So in terms of isogeny-based cryptography itself, it's not dead, okay, but it took a huge hit, and there are other options for that kind of realm of mathematics, that avoid that particular attack. Sure. But the important point is that designing secure cryptography in the real world is a really hard task. But it's also a necessary task. Like you can't just like not have encryption, right? That works for people. The internet itself is based around working encryption, right? Where things stay private. And we can be fun to work on this too. And so the thing I kind of want to point out here for like the rest of the talk is actually that cryptography from geometric algebra itself is actually an exciting research read. You have to proceed with humility, right? You can have great ideas and they can be broken. you have to work a lot, not only to develop whatever you're doing, but also to challenge your assumptions along the way. But the best key thing here, if you want to get into this area of geometric algebraic post-quantum cryptography, right, is to build these kind of broad collaborations with cryptographers internationally, as many as you can find. Okay. So I want to move into kind of this final part of my talk here, where I'm going to kind of go through a tutorial and we're going to get a little more technical, right? And talk about geometric algebraic post-quantum crypto, right? And I'm going to say there's open problems for years. And like, so I want to kind of highlight the underlying mathematical foundation of this, and then provide a couple, open problems, and then give you pointers to, where you can read more about this stuff. And also, of course, you can contact me if this excites you, right? So the fundamental question here is, could geometric algebra provide better post-quantum cryptography? And the answer I'm going to say is heck yes, right? So in particular, right, these kind of initial winners of this long process, this NIST PQC competition, which is genuinely the international way to get cryptography deployed. They're all lattice based. Okay, so there's kind of this notion of like, of the families of mathematics, the lattices were the ones that sort of like won out after all that time. However, and we'll get to this in a second, lattices are inherently geometric algebraic in flavor. They really feel like geometric algebra. The connection has not been made yet. So surely there should be a connection, and hopefully I will convince you of that. So what follows in the rest of this talk is an attempt, right, by me to kind of explicitly take lessons from, I'm not going to claim to be an expert in geometric algebra, but I will say classical geometric algebra, right at the foundation of stuff. And hopefully people in the audience here will, sort of have more expertise on this and sort of have insights to add, right? You can take lessons you've learned and potentially add it to lattice-based cryptography if you have collaborations with cryptographers and so forth. So I will show, right, in some sense, it's clear you can be more efficient with your post-quantum crypto. This is actually a good thing, right? Everyone uses encryption all the time, everywhere. Every time you log into a website and it says HTTPS, on Zoom right now, you're using encryption, I'm using encryption. More efficiency, great, we like that. It's less clear what the security situation might be when you start introducing geometric algebra to cryptography. But hey, that leads you to open problems. This is, again, a great, awesome thing. So here come the open problems. I have this nice slide here, like I said, I'm going to introduce classical geometric algebra. I'm thinking back to 1957, Art Ten's book about, in particular, he has main topics in this book, but one of the most interesting one here is, things here is orthogonal geometry, very fundamental mathematical concepts, right? And these things, I think, have not been actually applied quite yet to the modern post-quantum cryptography algorithms. Okay, so here begins the tutorial. Sort of trying to blend, if I will, lattice-based cryptography with geometric algebra concepts, sort of trying to merge the two topics, right? So first, step one of the tutorial. This is a lattice. Okay, great. It's always a pun. It's always, I think, you have to start any lattice-based cryptography talk off with. So instead of lattices, let's look at lattices, right? So a lattice is a set of all integer linear combinations of linearly independent basis vectors, right? So B1 through Bn, over the reals perhaps, right? And I have some nice equations there, but you can see this picture down at the bottom right. The idea is here, this is the two-dimensional version of a lattice. In general, lattices go to arbitrarily high dimensions. In practice, they go up to 1,000 dimensions, let's say. So here's in 2 dimensions, I can draw the picture for your slides. 1,000 dimensions, I can't. But in any case, the basis here would be, if you look at that picture on the bottom right, C1 and C2, right? So that would be like a, 2 integers or maybe 2 reals, and then, another column would be 2 reals, something like that. And the idea here is that given C1 and C2, I can take any linear combination of them as long as it's an integer linear combination, right? And that generates all the points in green, right? So I can string C1 into C1 into C1. That kind of gives me the line there. I can also take C1 minus C1 minus C1 minus C1. That'll go up and, up to the left. And also, throw in some C2s and minus C2s. Great. So that's a lattice. It's a set of points. It's an additive subgroup of the reals. There is this elemental hard problem associated with lattices, okay? It's called the shortest vector problem, SVP. So you're given a lattice, the lattice L, generated by a basis B. Again, I can actually step back and go, hey, the basis B here was C1 and C2. The lattice L generated by the basis C1, C2 is all the set of green points, and it's like infinitely large, right? So given a lattice generated by a basis, which is a fixed, like a matrix, maybe 1,000 by 1,000 matrix, or, in this case, it'd be like a 2 by 2 matrix, right? Find a lattice vector, not 0. And the lattice vector here will be B times X, just writing out the matrix vector multiplication, right? To represent that I'm taking an integer linear combination of the columns of the basis, right? And find a lattice vector that's not 0 with length at most lambda1. And in this case, lambda1 is the shortest vector, right? So you can see the picture here, you see the little red arrow, that's lambda1. And it turns out that shortest one, given the basis B1, B2, in this case, B1 being the first column, B2 being the second column of a matrix, you take an X and, Bx here will be 5 times B1 minus 2 times B2. And turns out that's exactly that green point right there that's closest to the origin of distance lambda1. In general, this problem is very easy in 2 dimensions. There's basically the greatest common denominator algorithm, like Euclid's algorithm kind of stuff, in 2 dimensions. But when you increase to larger dimensions, everything breaks down. Right. There are algorithms for this, but they tend to run in an extremely long time, particular exponentially long time, at least. For lattice cryptographers, we hope they run an exponentially long time. Okay, so when the dimension increases, the problem becomes very hard. Great. So I have a couple slides here about, 3 more slides or so, just talking about like something new. I want to introduce just some mathematics at an abstract level for the next 5 minutes or so. All right, so we're going to talk about lattices and isomorphism. So specifically, given any 2 lattices generated by some bases, when are they isomorphic? Okay, so we're going to say 2 bases B and B prime, right, in GLN. GLN here is n by n matrices, of course, with entries over the reals, right? They generate the same lattice if and only if there exists a unimodular matrix U, again, GLN, over the reals, such that B prime equals B times U. Okay, so it's a mapping from a basis to a basis. And if you have a mapping that's unimodular from basis 1 to basis 2, then they generate the same lattice theorem, right? In particular, just to remind you, a unimodular matrix is a matrix whose determinant is plus or minus 1. Particularly, the absolute value of the determinant of the matrix is 1. This is, in other words, a volume preserving transformation. There's something underlying here that says, hey, if I have a basis, the determinant of that basis for the, so basis B generates the lattice. The basis B for that lattice, the determinant of that is the volume of sort of the fundamental cell that tiles the space. So actually, let me step back here and say, think about, in this particular picture, there are kind of these like, trapezoids. Sort of, if you squint enough, you can kind of see them sort of tile the space. Okay, it's the nearest 4 points in 2 dimensions. Okay, so they sort of tile the space, and so the determinant of the basis is the volume of that fundamental region. So 2 bases generate the same lattice, right? If there is a volume preserving transformation that maps one to the other. Further, we can call 2 lattices isomorphic. 2 lattices are isomorphic if there exists, in particular, an orthonormal transformation O, sending one to the other, right? So this is the difference between the basis generating the lattice and the lattice itself, right? If you can have an orthonormal transformation versus having, a basis mapping to a basis. Okay, in particular, what does it mean for an orthonormal transformation O? What has to be an orthonormal matrix, right? Great. So you can take any lattice point, which can be described by a vector, okay, of dimension n, 1,000.
Daniel, 10 minutes to go.
Thank you so much. So I can have like a matrix and a vector, and I can like multiply any particular vector in one lattice by an orthonormal transformation, a fixed orthonormal transformation, and map it to, in particular, a corresponding vector uniquely one-to-one kind of onto in the corresponding isomorphic lattice. Okay. Okay, so further, lattice bases and isomorphism. Okay. So we're now going to consider, we have this idea again, looking at, two bases generating the same lattice, and we have two isomorphic lattices defined by an orthonormal transformation O. Bases are mapped together by this volume preserving transformation. Okay, so we can take two lattices L and L prime, right, and say they're represented by bases B and B prime. Great. And in particular, if L prime equals an orthonormal transformation O times L, right? L here is kind of representing any particular point in the lattice. Then OB, meaning that orthonormal transformation times a basis B, is a basis for L prime. Okay, this is sort of, in some sense, a straightforward, just mathematical calculation. It's not quite effective yet because I'm really operating with bases and using bases to generate lattices. But if two lattices are orthonormal to each other, then I can have an orthonormal transformation by a basis B and get a basis, some basis for L prime. Now, if OB equals B prime, right, the actual basis that I have generating L prime, then O, in fact, is B prime times B inverse. Okay, so there's this, you kind of figure out what that orthonormal factor is. But in general, the above kind of thing I've written there is only true up to some unimodular APU. That is, in general, overwhelmingly the case. If you, for instance, sample random bases and random lattices, in general, for some B prime, generating a lattice that's isomorphic to the lattice generated by B, B prime will equal OBU multiplication. So it'll be an orthonormal transformation, kind of a rigid shifting of things, if you will, times B times some volume preserving transformation. So I can, imagine what does a volume preserving transformation look like? Well, maybe I have a square and I sort of like shear it into like some long diamond looking thing, but I want to make sure the volume is maintained. So I can have volume preserving transformations that involve sort of shearing operations, and then sort of rigid transformations in some sense with the orthogonal stuff. And that sort of like gives you, turns out, a notion of generating isomorphic lattices. Okay, finally, last part of the tutorial, and I'm gonna wrap up the talk early. Thank you for letting me know about the 10 minutes. We're going to define the following problem. This is just a generic computational problem. Okay, we're going to call it the lattice isomorphism problem, right? So given a basis B, generating a lattice L, and also given a basis B prime, generating a lattice L prime. The goal of this problem is to find orthonormal matrix O, right, in the orthogonal, set. It's an n by n matrix that's orthogonal, okay, orthonormal in particular, with interest in the reals, right? And unimodular U and GLN Z, so that B prime equals OBU, right? So I know B and B prime, find the O and U that map these guys to each other. That's the computational problem. Okay. And it turns out that sort of this is an equivalence test, right? I'm trying to check if B and B prime generate equivalent lattices. It turns out that sort of testing equivalence in like GLR over GLNZ appears easy, right? It's sort of half the problem. So GLNR, of course, is where the basis B comes from. So if I kind of mod it out by GLNZ, I can test equivalence there. It's great. I can also test equivalence in the other side. I can say, well, like, GLNR over the orthogonal, transformation. That also appears easy. There seems to be like simple algorithms to do this. But testing equivalence simultaneously, right? B prime equals OBU, in particular in the double quotient of the orthogonals, divide on the left by GL and R, divide on the right by the integers, appears hard. And so this seems to be an actual hard problem computationally. And as soon as you encounter a hard problem, particularly in geometric algebra, you might start considering building cryptography out of it. Like this is a generic principle. If you have a nice crypto, or I'm sorry, if you have a nice hard problem you can't solve for your nice application, right? Turn it into a cryptography, right? So what's kind of the point? Ultimately here, right, here's the point. Typical lattice-based crypto doesn't do any of this stuff. It starts with a short basis B. Lattice points are BX for an X. The trapdoor basis B is hidden by scrambling into a bad basis A. So you take a short basis B that describes all the geometry in local regions. You scramble it into an A that is guaranteed to generate the same lattice, but doesn't give you short information. Like it doesn't give you like, you can't tell at a given point where the closest point is. I can only know points very far away. So I can only learn about local stuff. I cannot learn about local stuff. I can only learn about global information about the lattice. Okay, instead, what you can do instead of kind of this procedure of sort of like scrambling, creating a trap door, I know the short basis B for a bad basis A, I can publish A will let you encrypt, B will let you decrypt. I can consider the quadratic form Q, which is B transpose times B. I can consider bilinear functions X times Q times Y. Instead of BX, I can X, Q, Y, right? And this lit problem, if it's hard, then it's actually hard to recover B from Q. And the point is here is that Q is actually going to be much shorter in general than typical A from lattice crypto. And without going into the details, this gives you more than an order of magnitude speed up to post-quantum crypto, which is a huge deal. If you go back to like RSA that's been used for years, I don't know how big, ciphertexts or signatures might be, maybe dozens up to hundreds of bytes. Lattice crypto currently that's been standardized for post-quantum crypto is maybe 1,000, 2,000, 4,000 bytes. It's like an order of magnitude larger. So getting this last order of magnitude speed up in terms of the size of things and the running time of the algorithms is actually a real world concern. And I want to flash this on the screen. I'm going to pause for, please take a screenshot or something like that, or write down, these URLs, 2021, 1548, 2021, 1332, 2022, 1155. These are the three papers that will give geometric algebraists the intro that you really need. So in the last minute or two here, I wanted to kind of mention big open questions for geometric algebraic post-quantum crypto. Number one, without definition, since out of time, develop a homomorphic encryption scheme from the lit problem. There exist homomorphic encryption schemes from lattice problems and relatively nothing else. But this is an area where geometric algebraists could get into homomorphic encryption, specifically by focusing on this lattice isomorphism problem. Second big question, right? I've defined a mathematical problem, solve it, right? Please try and solve it, right? Break the weak math problem, right? You don't think this was a hard problem? B prime equals OBU, find O and U. Great, go solve it, please. There's also really interesting mathematics, particularly in the papers I just cited about the genus of the quadratic form in a ring. Really, really deep stuff, really fun stuff, and really untouched stuff, but actually stuff that's important. And finally, third big problem I'm going to mention here before I conclude is, there's also this idea of like how do you argue that a scheme is secure, and talking to a non-cryptographic audience, 30 seconds is not enough time. But I will simply point out, you can give a reduction from the lattice isomorphism problem to the short vector problem, or from the module lit problem to the module SVP problem. And this is sort of going to mirror Regev's reduction, REGEV, Regev's reduction from LWE to SVP. That's a third really big problem that is open and doesn't seem to be hard to solve, although difficult to solve. Like hard meaning like it's possible to solve, but a very difficult one would be a big result and seems brand new and very possible. So just to conclude really quick, covering the whole talk, thank you for listening. The transition to post-quantum cryptography is happening today, right? RSA is dead. Long live lattices. Within 10 years, no one will be using RSA anymore. I promise you. It sounds weird. It's been around since the 70s. It's been around for many people's entire lifetimes. We're going to post-quantum crypto. Second, be very careful with your cryptography, right? Consult with experts. Find people, the broader audience you can, the better. Even very appealing schemes in cryptography, very beautiful mathematics can be broken very suddenly and totally. That's a major lesson for this last 7-year process. And finally, I really do believe that geometric algorithms have a lot to add to modern cryptography, right? It's right at the edge of things. This is right the time right now. There are hard problems to solve. And you should, if you're interested in this, try and actively build research collaborations with cryptographers. And thank you very much for your attention. I'll take any questions if we have time.
Thank you, Daniel. We have a question from David.
Hello, Daniel. It's David Silva. Thank you very much for your fantastic talk. And I think it's refreshing to hear from someone in the crypto community to declare this positive look into geometric algebra and recognizing the possibility of geometric algebra bringing something new to cryptography. We talked about this before, and I know that you don't have time to go deep in the weeds, but you mentioned that this type of mathematics could give to crypto, like could represent, like from this type of mathematics, you could have immediate security, like in the CPA security, and like additive homomorphism would be immediate, and even multiplicative homomorphism would be immediate through some type of tensor product type of operation. So first of all, I have two questions for you. So the first one would be, can you speak a little bit more about your current thoughts about homomorphic encryption being derived from GA, and overall thought about that? But also, did you consider the geometric product realizing multiplicative homomorphism?
Were those the two? Yeah, so I can say, we have also interesting questions in chat. So the first thing I'd say is, the first thing that one has to do to get homomorphic encryption is ensure that you have a basic, well, homomorphic encryption implies public key cryptography. You have to therefore begin not just private key, but you have to begin with in some sense, a public key encryption scheme that you believe is secure, definitely. And it has to go, oftentimes when you have, a particular, option or suggestion for how to build a public key encryption scheme, it has to undergo, first of all, sort of the rigorous analysis of like, the generic stuff. There's certain generic principles that you have to, you can just check off real quick. The second thing would be the underlying hard problem. And I'm happy to actually talk with you, David, about that. I think, that you talked about the wedge product. Did you say what was the particular
Geometric product?
Geometric product. I'd be happy to talk more about that offline, actually. So I think it's going to be a deeper topic that I can answer very quickly.
Okay, there are, Daniel, you can probably see there are three questions on the chat. First from Eckhard, has any work been done already on quaternion lattices?
So the answer there is yes and no. So quaternions tend to appear not in lattice-based cryptography, but they do appear in post-quantum cryptography, I guess towards the isogeny field. In terms of quaternion lattices, again, please, my emails are right there on the screen, hopefully still. Please email me about that and I'll be happy to look into it. But in general, no, there is sort of a goal of unstructuring the lattice like as most as possible to prevent so the idea is that structure tends to give you efficiency, but structure also gives the adversary, the attacker against your scheme, additional efficiency. So it's always a balance between structure and unstructure when you're designing kind of crypto systems. So I don't think quaternion lattices have been explored. There's maybe a paper or two on ePrint, but they haven't really been picked up as the answer to that one.
Okay, and Hamish has a question. Has any lattices in non-Euclidean spaces ever considered? Presumably spherical or hyperbolic.
The answer is no, but I'm interested to hear your thoughts if you want to email me. So the idea fundamentally, if you want to do lattice cryptography, so sure we have this idea of a lattice, and I didn't even get to this in this talk, but what's the hard problem? The hard problem is sort of a notion of shortness, of blurring a lattice point with Gaussian noise. Sort of, in high dimensions, it'll become a hypersphere, right? But the idea is you sort of blur lattice points, and it's then a hard problem. The notion of shortness sort of requires a norm, and it's typically the Euclidean norm. It's like the L2 norm.